Okay, in this video we're going to be talking about concentrations, or units of concentration. So different ways to measure how much solute is dissolved in a solvent at any particular point in time. We're going to start off with a couple of vocab definitions, and then we're going to get into 4 different units. Each of the 4 units will have its own slide, so you can avoid what's going to be at the bottom half of the next slide, because we're just going to go over them individually. All right, you are going to need something to write with. You are going to need a calculator, something to write on. A periodic table might be helpful, but I'm just going to kind of do these as examples. Once you have all those ready, let's go. So again, concentration, the definition of concentration is how much solute you have dissolved in a solution. Now, we have a couple of terms that we use, concentrated and dilute. Concentrated means you have a lot of solute dissolved, right? So for example, concentrated sulfuric acid has 12 moles of sulfuric acid for every 1 liter of solution. So that's a very high concentration. While a dilute sulfuric acid solution would have like maybe 1/10 of a mole of sulfuric acid dissolved in a liter of solution. Right, so concentrated means a lot, dilute means a little. And then we have our units. We have percent, which you'll see sometimes referred to as W over W, meaning percent weight by weight. We have parts per million, which you've probably seen before. And then we have the 2 units we're going to spend the most time working with. Molarity, which is going to be our default unit for concentration. And molality, which I'm going to show you now because it will become popular for a video I'm going to show you in a little bit. So for percent by mass is the same thing as percent composition, right? So mass of the solute divided by mass of the solution. Most household solutions that you see are going to be given to you in percent. So for example, a rubbing alcohol solution, when you buy rubbing alcohol at the store, you either buy 50%, 70%, or 90%, meaning that it's either half rubbing alcohol by mass, 70% by mass, or 90% by mass. As an example, we have hydrogen peroxide. Household hydrogen peroxide is a 3% solution. So if we have 500 milliliters, and the density of hydrogen peroxide we're going to assume to be the same as water, right? So 500 milliliters means 500 grams. If we have 500 grams of hydrogen peroxide solution, and it's 3% peroxide, how much peroxide is dissolved in the solution? Well, we have a 3% solution equals mass of the solute, which we don't know, divided by 500 grams of solution because the density is 1. We solve for our unknown x, and we get 15 grams. So 500 milliliters or 500 grams of household peroxide has 15 grams of hydrogen peroxide dissolved in it. Right, so that's percent by mass. Very easy, very straightforward. Math works the exact same as percent composition. Our next unit is what's called parts per million. This is actually very similar to percent by mass, except instead of dividing the mass of the solute by the mass of the solution in total, you divide the mass of the solute by 1 million grams of solution. That's where the part per million comes in. Amount of solute per 1 million parts of solution. Where you typically see this are things that are very, very toxic in low concentrations, right? So when they measure the amount of carbon dioxide in the atmosphere, they tell you that right now, as they're recording this video, it's approximately 420 parts per million. So 420 grams of carbon dioxide per million grams of air. Similarly, you have a smaller unit that's called ppb, or parts per billion, where instead of the denominator being a million, it's a billion. These are for things that are extremely hazardous in small amounts. For example, like how much cyanide you can take in without actually dying. That is measured in parts per billion. It's actually measured in fractions of a parts per billion because it's that toxic. We won't really use parts per million that much in here. I just wanted to kind of go over it so you've seen it before, and that way when you see it like on a news report or something, you have some idea of what it means. Now for our default unit, molarity. Molarity's variable is capital M. Molarity is defined as the number of moles of solute divided by the volume of solution in liters. Right, so this is what we're going to work with more often than not. There's also a form of this called millimolar, which is moles per milliliter of solution, which may be easier to work with for some stoichiometry problems when we get to them a little bit later on when we cover acid and base. So do keep that in mind. Now, the main thing about molarity is that it's volume of the solution, not volume of the solvent. The reason why is because when you add a solute in, that will change the overall volume of the solution, right? That volume had to go somewhere. So if I pour like 100 grams of salt into a couple of hundred milliliters of water, that salt's going to take up a fairly substantial amount of room. Right? So we want to account for that by just taking the volume of the solvent. So we'll do an example problem with this. We want to make a sodium chloride solution. So I want to know what mass of sodium chloride we need to make 335 milliliters of a 0.2 molar sodium chloride solution. First thing I need to do is, remember, molarity is moles per liter. I need to convert milliliters into liters, so 0.335 liters. And then I set it up. Molarity equals N over V. So 0.200 equals N divided by 0.335. That gives us 0.067 moles of sodium chloride. Now that we have moles, we want to turn moles into grams because it's asking us for mass. To do that, we're going to multiply by the molar mass, which is 58.45 for table salt. We plug that in, and we get a mass of 3.92 grams of sodium chloride. So to make this solution, I would take 3.92 grams of sodium chloride and dissolve it. Okay, so that's molarity. Moles of solute per liter of solution. Molality, which is lowercase m, is a little bit different. We won't use this that much, but we will use it for something called colligative properties, which will be a couple of videos from now. It's still moles of solute, but instead of volume of solution, it's per kilogram of solvent. The reason why is, you know how I said that the adding a solute will change the volume of solution? This unit will completely ignore that. Right? So it only matters how much solute you have, how much solvent you have, not how large the solution actually is. Now, for some of these problems, and we'll get into these when we do examples, you may need to know the density of the solvent or the solution in order to actually work with it. And one thing to keep in mind is that because solutions may have a different density than the solvent that they come from, molarity and molality are not interchangeable units. All right. And then the last thing I want to cover here is a specialized equation that we're going to use when you dilute a solution. Right? To dilute a solution basically means that you're going to add additional solvent. If you add more solvent, that means that the concentration of the solution is going to go down. Right? Concentration and volume are inversely proportional. Just like we did for gas laws, if the variables are inversely proportional, we'll multiply. So we're going to get M1V1 equals M2V2, where M is the concentration and V is the volume. Now the good news for this is that just like our gas laws, as long as the concentrations are in the same unit and the volumes are in a similar unit, it doesn't matter what you're working in. Alright, so you notice this equation looks a lot like Boyle's law, P1V1 equals P2V2. That's by design. So for our example problem here, we start off with a 300 milliliter solution of sodium chloride. So 300 milliliters is our V1, 2.5 molar is our V1. Then we add 1500 milliliters of water to that. Now, here's the trick. 1500 is not V2. Right? I didn't say we were diluting it to 1500. I said we were adding an extra 1500. So our V2 is going to be 1800 milliliters because the 300 we started with plus the 1500 we added. So V2 is 1800. We're solving for M2. Plug into the equation, rearrange for M2, and we'll get our new concentration of 0.417 molar. So that is a dilution problem. In our next video, what we're going to go over is we're going to go over the process of making a solution. I'm also going to include a little bit where I actually do go through making the solution. So I will see you guys for that video.